giving me this opportunity. It's my first time in Scotland, and the landscape have been quite striking. Like even from the train from London to here, and yeah, next few days, I'm looking forward to walk around. And this is some topic like been studying with Skinner in EATM for the last few years, and recently we have completed we posted this month, and it's also like Shinwan is joined couple of years ago, and I'm afraid it's maybe the most elementary talk of the conference. There will be no phi gamma modules, like no stacks. I, yeah, I'll start just with some application. See, basic arithmetic object is we just start with an elliptic curve for rational numbers, and as we know, like the key at least of primary, we enter the rational points which we the rank is model weight theorem is finite, and uh, which is conjecture, and the BST conjecture predicts mysterious links among those, and like a primary and analytic object, which is the Hasse L function, a functional equation with center at s equals 1. Fundamental result towards the BST is the Gross-Zagier and Kolyvagin theorem, which is if the central order of vanishing is at most one, then the rank model way rank is the same, and choice. First breakthrough towards this is due to code files, and then have been in the CM case. But yeah, sorry, just for brevity, I'll only mention write this. And there's something. One can ask like many problems, but let me just state, sorry, two problems. Um, so first is so say like at least in this at most rank 1 situations, like once we the arithmetic invariants are at least qualitatively look like what one expects, like one can ask the further quantitative form, which is the BSD formula in such like at most rank 1 situations. And the other is somehow like so-called converse to. So yeah, just like here, when starting with some information on the analytic side, and one can in practice, like one, for example, one might be computing some Selmer groups, and maybe like sometimes at least or it's a basic question in. Sergey and Kolyvagin, and yeah, actually, like over the last decades, over the last decade, there have been various results towards these two problems. I will say something about those results as we go along, like just some indication. Um, And there was a sort of a maybe initiated by Chris Skinner and Weisman. I But let me just start by stating like one of our so like the results I'll state are joint with them. I'll not write. Yeah, like yeah. Sorry. So E over Q as before, and conductor like just maybe we'll use this notation like N. And it's like let's take a super singular prime which is away from P. Good reduction. Yeah. See, and it is super singular. Then the result is like if the central vanishing order, like so, yeah, like if our analytic is at most one, then the P part of the BST formula holds. That is just right, the after yeah, like the leading term of the L function in this case, like just first derivative or the L value itself, and then some normalization of period. And in the rank one case, there's also a regulator. Which after Grossaghe, we know this is an algebraic number. So it's the analytic and the key invariant on the arithmetic side is the in this context is the type size of Tate Shaffray, which can P part times the Magawa. So sorry, this is a square free. I forgot a key assumption. That's there's no torsion here. It's a super singular case. That's the yeah, that's the first. And maybe let me just say in words that so say like in particular yeah there was okay so I just mentioned so in the R like in this the I'll just mention a couple of remarks on the prior work like if R is equal to one then there's another there is a word for which is due to sorry J. Skinner one. And but actually it relied on the R equal to zero case of this theorem. So if you like the strictly speaking, the new case of this result is R equal to zero, but the previous work in the R equals one case relies on this result. For quadratic, so not literally for this quadratic, certainly. And, yeah, the square free assumption excludes, like in particular, it excludes CM elliptic curves. But we know more like the CM curves more is known. For example, the R equals to zero is actually now complete. Like we have the complete BSD formula, at least in that case, like, and R equals to one also, one knows more. I'll not say it precisely, but yeah, it is not completely. R equals to zero case is complete. And yeah, I'll mention some application of this theorem, which is
Did you mean to write something R equals after R equals one?
sorry, I should, yeah, sorry. Yeah, sorry. Sorry. Um, so like at least like so in the R equals to zero case, like the CM case, like we have complete. But in contrast, like the non CM case, like if one wants to prove the full BSD conjecture, so in particular one has to treat like all primes P, like not just like particular prime P, but even for a fixed elliptic curve, if one has to show the full BSD, then this has to be shown for each prime P. And no, that's the next, but that's in a very special case. This is some 46 A1 in the LMF DB. You could take this particular semi-stable, this has rank 0. And yeah, this BSD conjecture is true for infinitely many quadratic twists of E.
The BSD formula.
Yes, BSD conjecture, yeah. But yes, the main content is in the BSD formula, yes. And yeah,
So what moment? So for infinitely many quadratic twists, I mean, are these the cases when the rank is 0 or 1?
it's actually 0, yeah. Yes, that's good.
Oh, okay.
So it is the rank, yes. Yeah, yes. Yeah.
I was just wondering whether you could say something about higher.
No, nothing, yeah. Yeah, so actually, yeah, that's Sarah commented, so. It's just rank 0. All members have rank 0. And but I maybe just to indicate actually, so it's really like a culmination of like various previous works. Like I mean, this is just some piece, like some small piece of this result. And yeah, so like yeah, one has to if as we have seen, like the rank is 0, then you know one has to show this formula for all primes P. For any member, like one has to prove the formula for all primes P. And actually this is a sort of maybe an interesting history. So if P equal to infinity, it's already a non-trivial statement. Like it's saying that the L value is non-negative. And this was actually proven by Konen and Zagi in the early 80s. So in general, like not just this case. And yeah, and then we have different primes of reduction. Like one has typically applications like this is periodic in nature and quite sensitive to the type of reduction of E at P. And yeah, when P is an ordinary prime. greater than 2, then this was a largely due to Skinner. Yeah. Um, and P is super singular is like that's where like this result gets used, and as we know, like super singular is some infinitely many, there are infinitely many super singular primes. And there is also a case like when P is equal to 2. And so yeah, some yeah, some were yeah, and so actually like yeah, these are Iwasawa theoretic methods, like I'll say, so some yeah I'll say here, but P equal to 2, that's where actually like some specific nature of the family, like some example, like what something like this is, Yetian had some observations for some particular type of curves which are not Iwasawa theoretic in nature, but and yeah, before this theorem, like for non-CM elliptic curves, the BST conjecture was known only for finitely many examples. Because no matter what example one starts with, one has to handle the super singular primes. Um,
The primes of what's the production type of the elliptic curve? So it's split multiplicative at all.
Yes, yeah, there is also multiplicative. Yes, yeah, one has to also handle multiplicative primes, and this there is a paper of Chris which handled the multiplicative.
That's the only batch reduction type of.
And there is also the case of like additive reduction, like which is a delicate problem, and like so somehow by so actually like I stated the theorem for semi-stable elliptic curves, but it's also okay for quadratic twists, and so at least like certain type of additive reductions are okay, and there is some, yeah, okay one has some, but that's not used here, like it's only this, like yeah.
Because that one doesn't have.
Yeah, this is a semi-stable curve. Yeah, yes.
Can I just ask out of curiosity, in this family, are both sides of the formula two-adic units, or is there really a power of two?
Yeah, actually, like for some quadratic, it's the two terms is maybe z. Yeah, actually, like yeah, like it's z mod 2, like this curve, like the
Oh, it has
version
two
of z
versions.
mod 2. So one,
Oh, okay.
yeah, one has to check something. Right. Yeah, yeah, so like yeah, this is purely like some statement about the elliptic curve over Q and like some feature, and the so far the methods to attempt to approach such problems are largely even
Sorry, so what's so you didn't say like what's the specific property of this curve which makes it work?
Yeah, so I did not specify, like someone has to also check the formula at P equals to 2. And like so like these results are theoretical in nature, but Yetian's is not so much theoretical. It's something one can verify so far. And so in this particular setting, the framework of indicate yeah, so some the shape of Iwasawa theory, or where one look for in some ways it actually appeared in David's talk yesterday, but yeah, here is some I'll try to be brief, and yeah, so let's actually yeah, like so yeah, that's some maybe basic principle of Iwasawa, Maser, and various people. So like yeah, this is some equality about like p parts of some invariants, and somehow like if one can consider variation of both sides in certain periodic families, and yeah, and then one maybe like if there's a systematic expectation, like this is really something like what is for a given curve at a given instance of time, but maybe if there is some variation, periodic variation, and maybe more concretely, if one can really guess the shape of how the periodic variation looks like, then maybe at least like that can give more tools, because it's potentially like there's some family. And so I just briefly recall, so it's again just the same and this is a super singular, and the variation one considers is, I mean, it's a periodic family, but maybe of the simplest kind. One can imagine like it's the, so sorry, so Q infinity is like this ZP cyclotomic extension, and like it's the yeah, okay, yeah, and it's the US sorry, gamma, like let's just say gamma is the Galois group. Um, like the other deform, and let's just let like P denote the Tate module, periodic Tate module. Then yeah, just the deformation considering it's just the twists of, yeah, just the twists of the state module by characters of this ZP, yeah, twist, and just compact way of saying this is like we consider some T tensor lambda, this is capturing the twists, and for some reasons it's considering dual is. And and just as one has the Selmer group, like for a given certain yeah, like for a Tate module, for example, I mean, we have the Selmer group. There's also,
What are you taking Hagen dual of lambda, or what is it?
yes, it's a pond thread. Sorry,
And are you excluding P equals 3 just because AP might not be 0? Would it still work for P equals 3 if A3 is 0?
yes, it's yeah, I'm just for the writing, and yeah, like, yes, yeah. And actually, it turns out that yeah, I just maybe I'll mention quickly. So if one tries to consider like in the one has the notion of like Tate-Shafarevich group, and any number field, and in particular one can consider like along the towers of extension, and yeah, like so actually somehow like what kind of Selmer group to consider is actually, so yeah, although I mean the module is some very transparent like what one is looking for, but on the arithmetic side, like what Selmer groups to try to define was a problem for quite some time. And Shinichi Kobayashi in his thesis, like he I'm sorry, I'll just indicate like notationally at first, like, but for certain signed Selmer groups, which sorry, yeah, okay, yeah, it's is the like the first cohomology like unramified outside finitely many places, and yeah, like the module like one we have, and then yes, the condition, a local condition. So away from P, just like we are putting the sorry, L in sigma L not equals P. It's just the like yeah, 0 like one. Sorry. And yeah, at P, Kobayashi defines certain signed certain signed submodule, which I, unfortunately, because of time, I'll not say more, but I'll indicate some aspect. Um, and yeah, this is, but I'll just say, like, it is not the block Carter local condition. Like, if the block Carter local condition is actually zero in this family, and yeah, sort of his insight was how to define. And yeah, and then again, it's maybe strange if you have not seen it before, but one again takes a dual. Um,
Away from P, it's IL, the inertia.
it doesn't matter. It is what is written. And yeah, and, I'll first just state the conjecture and then say more about the object appearing in it. But yeah, the Kobayashi, like, after defining this, like, yeah, he proved that this is a torsion. Firstly, like, this is a torsion lambda module. So at least, like, it has a some control. Um, and yeah, yeah, actually, like, so prior to this, like, Rob Polak, on which, like, Kobayashi's work was inspired by some construction on the analytic side, and I'll say something about this soon. But yeah, like, some there is some periodic L function. And yeah, it generates it. It is an integral object, like in lambda, and it generates the characteristic ideal. Yeah, it now and yeah, it is the periodical function interpolating the L values one would expect, like finite order twists, but how to normalize it was how to integrally normalize was experimentally found by Rob Polak also in his thesis. Yeah, which preceded Kobayashi is yeah, so I will not be completely precise. Yeah, like when we evaluate it at some finite order characters, it's the some factor which was the key. So some factor dependent on chi, or I'll say what that factor is, and times the L value, like E tensor chi inverse or omega E. And so it's actually, it's some half cyclotomy polynomial. I'll just say it in one case, like, so let's so uh let's say to say, yeah, somewhat concrete, I mean, yeah, concretely, like, let's say chi is of order p to the t. I mean, so sorry, I did not say chi is a finite order character. Finite. And yeah, chi of order p to the t, then this factor EP, I'll just say it for the plus part. It's up to some, there are some constant like this depending. And then there is a power of p over some norm, some Gaussian. Okay, and here is like now the some other some is the main part which is half cyclotomic polynomial, which is phi the Zeta inverse where m is odd, m goes from 1 to t minus 1, but m is odd. And this is like when t is even. Yes, yeah, just yeah, there is some somehow dependent on whether like t is even or odd. One like Rocco like found like this factor and proved like not only found it, he then constructed. So yeah, and I. So maybe yeah, this is strictly speaking it's greater than 0 even. And when t is equal to 0, there is some correction. Yeah, so at least like one can see like so we are dividing like one can see in particular we are dividing the L value by the values of like such half cyclotomic polynomials. These are highly divisible by p. We are putting zeta is p, so and like I should have said like zeta is p to the root of unity. So say like we are dividing the L value by some quite high powers of p, and after such division like one Rob found some integral object. And yes, and actually the result is like so we. Yeah, like that is the Kobayashi's main conjecture is true in the same state of.
So, I mean, one inclusion follows from Cato's work, right?
Yes, yeah, the main yeah, the only content is the other inclusion. Yes, yeah, thanks. Yeah, yes. Yeah. And yes, yeah. Yes, say this. And so I just maybe make a brief remark because some related also main conjecture.
Not 2 and 3 was.
Yeah, you already assumed, but maybe yes, yeah.
Yeah, P doesn't divide 6n.
Yeah, but yeah, actually, yeah, in David's talk yesterday we saw Pothurst like main conjecture formulated using triangulation, and I just so I'll just make maybe a couple of remark. Yeah, and the triangulation depends on the choice of eigenvalue. Like we have two eigenvalues, but there are two main conjectures, and here also there are two main conjectures. Like circ is plus and minus, and actually like somehow they are equivalent. Like the pair of those pair of main conjectures are equivalent. So actually, yeah, there is some linear algebra, like how to go from one to another, but which was a key insight of yeah, both maybe both us and Poland. is equivalent actually to conjecture P, maybe that's P. I don't know, I forgot the notation yesterday, but maybe P down with the eigenvalues, like the Hicke eigenvalues.
Is this really true? I mean, surely that conjecture is equivalent to that one with P inverted, which is a substantially weaker state.
Oh, yes, so
Laplace main conjectures are always with P inverted,
Integral, yeah, that's
always
true.
non-integral.
yeah, thanks.
Does the Kobayashi Selma group actually coincide with Potthast's Selma group when you invert P?
No.
No.
So they're not even over the same ring. One's over distributions, the other over measures.
In some sense, yeah, related by quotient. I mean, but we can discuss it later.
Yeah, like the coefficients are already robbering, like some, yeah, like, but here it's an integral, even Saval algebra. And then maybe an interesting, to me, an interesting point is like usually like integral constructions come after the unbounded constructions. But in this case, it was somehow reverse. Like Kobayashi found like this framework, like even before the existence of triangulation was proven by Kissin. And I just maybe another sorry another agreement actually like this conjecture okay Kobayashi's main conjecture implies the P part of the BST formula. If R is less than or equal to 1. So the theorem which was stated before is actually just a corollary of this. And yeah, and actually like yeah, this is the R equals to is actually just the descent of the Iwasawa main, the descent of this main conjecture. And so like on both sides, like this L value, sorry, the periodic function is already encoding the L value and it's spatialized. And but yeah, R equals to 1 case is more also December, but now like some regulators are involved, like one rank one situation, and they relies on the not yeah. So this is actually also it relies on periodic Gross-Hagier of Kobayashi. Also, plus like some non-vanishing of periodic height. Of non-torsion points. This is a theorem in the super singular case, but the ordinary case is still a conjecture. Yeah, and now yeah, and I forgot to say that this was actually announced by Shinwan about 10 years ago, but it's now come. Some sketch. Assuming something exists, yes. And yeah, and actually like it is like the central maybe of our studies, like existence of some zeta elements and no imaginary quantities and yeah, the Kobayashi's main conjecture is over Q, but somehow working or imaginary quadratic fields like allows some flexibility and I so I now maybe here choose so, okay P is not necessarily prime of or sorry P is not necessarily super singular, just to try. Yeah, but K is an imaginary quadratic. Some maybe I'll probably forget one key assumption is like P split. With P split, and maybe there are some I probably forgetting, but maybe there are some conditions. Yeah, maybe or sorry, maybe let me just say maybe like a no P torsion on E over K. And just as there is a some framework like over Q in the P split is there is also yeah, there are main conjectures over imaginary quadratic fields. And be sorry, I'll be quite but I'll just like say refer to some at least some underlying objects like which and so like Polak's periodical function, like there is a analog over imaginary quadratic fields like which David like constructed by David in the super singular case. Yeah, like but maybe I'll use like some notation for brevity. Maybe I'll use like some dot, maybe in P ordinary. This minus super singular. Just some notation. Then there is first one has like some periodical function. Sorry, E over K. Lambda K. Yeah, integral. So sorry, I should yeah, like so in this case the Iwasawa algebra is ZP so yeah, the Galois group is gamma K is the Galois group that's isomorphic to ZP square, and there's this notation like lambda K. So algebra now it's two variable power series in non-canonical. And, um yeah, the first is yeah, some quite similar to what we have seen before. Yeah, for chi finite order. It's one object, and but yeah, like one over imaginary quadratic fields. Like, in the infinity type of Hecke characters, the pair of integers, and this is when that pair of integers is 0, 0. One can consider other other ranges, and yeah, then there is another yeah, like so this is something like in the super singular case, like there is some modification as indicated, but curiously, like in the other case, like it's independent of whether ordinary or super singular. There is um some slightly scalar yeah, there are various yeah, sorry, I'm yeah, not highly aware. No, here's like some other so, yeah, for chi infinite order, certain particular infinite order, but I'm not some infinity type. And then the period is like some power of CM period depending on the infinity type. Then yeah, yes, and like that's would one can ask for one expect is like the main conjectures for these periodical functions, like yeah, and they do seem quite different in nature. So Yeah, sorry, the labeling is not, but yeah, the first is the first periodical function now there is an analogous Selmer group like defined um, um, and adapting Kobayashi's definition. And, yeah, so not in the ordinary case, the condition is just the block out of local condition, but the and here the local conditions now depend. So actually here one is there are two primes above P now, like and at both primes here one is putting either odd local condition or like plus minus plus comma plus depending on the sign. But now here is like the local conditions are very different. Like that's at first prime one is putting no condition, and at the second prime yeah, the classes to vanish like strict condition. Um, s- um, and yeah. So like at least from global consideration, these maybe have quite at least apparently maybe different nature, and but one can ask like are they related? Again, like you can see the disjoint, like at least from the constructed and also from the consideration of local. But yeah, Kato has a very general conjecture on existence of Zeta element on which there has been a lot of progress as we heard from yesterday, and I'll also comment more later. So surprisingly, at least at first glance, surprisingly enough, like this very general principle of Kato in this particular case predicts that these two are actually equivalent. Assuming some Zeta element exists. And yeah, now say the yeah, what is this Zeta element? And which is actually the main theorem. Yeah, the result is there exists some Zeta element. So somehow again depending on the type of reduction, but you can at first one can just view it as a decoration, like as something associated to E over K in the global Galois cohomology. And here the condition again at the first prime it's no condition. At the second prime it is the condition depending on some either ordinary or super like something but something plus minus. But I just so that's a different condition. And yeah, like and this is over K, like we are working over K. Yeah, and the what is the underlying module? It is again the Tate. And now for the Zeta element, it lives in the with compact coefficients like the Tate module tensor lambda k. So like there, yeah, the Kato, the predicts like there is a zeta element is at least like in it's one out there to live in some global Galois cohomology, and which encodes like both the periodical functions. Like in general, he predicts the zeta element to include L values, critical L values in a family. Yeah, but yeah, like so how is it related to L values like such that so it's again like there are yeah, it depends on the both primes above P. So that at the first prime, like so sorry, I forgot, but yeah, like let's just say P is like V bar. It is split. So some like some Coleman map is something interpolating dual exponential maps. Yeah, but one can first just think of this as like yeah, like at first prime, like the localization at the first prime, and then applying certain normalization of the block-Kato exponential, like this recovers our first periodical function. And at the second prime, it is actually related to logarithms like block-Kato logarithms like log v bar. Of the same element. And, yeah, and yes, so that's the and yeah, like so we just say so say actually yeah, the zeta element allows in particular it allows flexibility, like because yeah, the as you can see the main conjectures have quite different nature, and but via the zeta element one can like maybe sometime at least for some purposes like some main conjecture one maybe has more tools like for example like the conjecture tool it has been studied by previous works of Shinwan, like conjecture tool, like he studied some based on Eisenstein congruence on the unitary group U31. So at least like some of this is, although it is a super singular situation, like for the purposes of Kobayashi's main conjecture at
Okay. So I guess that the construction of your zeta elements, I mean, relies on the order system we construct.
yes, I'm going to say this here very soon. Yeah, yes, that's yeah, central, yes. And I maybe yeah, sorry, I'm yeah, maybe low on time. And I'll just so
Greenberg.
yes, Shimon, I think, some results on towards conjecture too, and yeah, why are the zeta element plus work of um really, like, yeah, Kobayashi's main conjecture, like it's one somehow yeah. So I can say more later if you're and yeah, me just point to there are also some other uses of zeta element, like not only the super singular case, but for example, yeah, there is a work of this Castella, Grossi, Skinner in the Eisenstein case, which is the ordinary case. And also, as David mentioned yesterday, there is a work of Fouquet and Wan at the additive prime. For that again, like zeta elements are they're an ingredient. And yeah, I want to say something about the existence, which very heavily it's based on work of David and Sarah. I um yeah, so yeah, actually so they have a series of works on the Rankin-Selberg zeta elements associated to pair of like f comma g, like pair of forms, and sorry, maybe I only said yeah. As we have time, I'll say more Rankin-Selberg zeta elements. But maybe I try to say like also what is the new yeah, what are the aspects one need to analyze, like yeah, their work is the kind of the start, if you like, something like engine of the construction. So like so actually like how do Rankin-Selberg data elements, or why does the Rankin-Selberg convolution arise in the first place? Yeah, actually like there is a some given in like this our imaginary quadratic field K with P split. Yeah, actually yeah, so we have the in some ways like a canonical object is the just the quadratic character associated to the imaginary quadratic field. The weight one, I mean, yeah, it is a theta series, weight one theta series. And it is P, or weight one is ordinary. And and there is a family, actually one can write down a canonical family like Hida family passing through this weight one. Maybe I denote sorry, maybe let me just say H. And yeah, actually, so this is an Eisenstein, I mean, the associated Galois representation, if you like it, just the induction of the character. So it's just like one plus the character. So yeah, in fact, this is Eisenstein. And yeah, and also yeah, and like the Hecke algebra, like the Hecke at these particular primes is actually non-Gorenstein. This was also quantified by Mladen in some work. So actually we um you're mm, wait, you know, David. And but yeah, like so that's the just so how does like yeah, I I'll just take a few, sorry, few 3 minutes or yeah, like the David, Sarah, and like the various works, like they give construction of the Rankin-Selberg zeta element, if you like, associated to Fe, like the new form associated to E, and this like the this particular Hida family. And yeah, and this is yeah, their zeta element is so I will assume like ordinary, like suppose like P ordinary for now. Yeah, like their Zeta element is over Q. And yeah, and again the coefficients are our T, like the initial Tate model of elliptic curve, but now it is tensor with like some sorry, and tensor lambda, like the cyclotomic so if you like, this is some kind of HIDA, I mean, it's the Galois representation associated to the HIDA family, and this is the cyclotomic variable. And let me just say, actually, so this comes from the cohomology of open modular curves. And actually, like, so by the series of works, actually, like this does have like the correct reciprocity laws. And but now the problem is like we do not quite know like what is the what is H, like what is this Galois representation, and and what one might expect, like, or at least like naively, like, so this is something like a HIDA family passing through, like, yeah, just some CM4 or Eisenstein series. So the first guess might be that the associated Galois representation is just the induction, like some induction of the some family, like, yeah, one just deforms this in a suitable precise family. But so But the problem is by the way this is defined, like it is coming from open modular curves, by the way, like because it's based on the Ziegel units, and Ziegel units are naturally, yeah, that's where the first contribute. And yeah, the first problem is we are asking whether it is induction, but the first problem is it may not even be a free as the
Not cuspidal, huh? It's over the whole.
hospital. Yeah, actually, because it's somehow Ziegel units are yes. So let alone like ask the question about induction, like it's just not even defined the question in general. Yeah, I'm almost done. Yeah, sorry, I just and yeah, and yeah, like so as now then was alluding to, like, yeah, there is like this sort of open lattice, but there is also, or I mean, like, sorry, I should not say lattice, but just what comes out of geometry, and then there is also like the cuspidal part. Just, yeah, where one works with the full power of modular curves. And and to begin with, their Zeta element lives in the sort of like this open lattice. But our sort of the key and I'm going to stop like after writing this. Yeah, there are two results. Like the first is yeah, like that so maybe sort of strangely enough, like although the Zeta element by construction lives in this open lattice, but actually like it lives in the closed lattice. That's the first. And again, like those are different, like we are in an Eisenstein situation. And the second part is we still don't know whether like this one is induced or free, but yeah, this one we show that it is free and induced. And yeah, so sorry for going.
There are some questions.
I was just ask, so free here means free over the Heck algebra, or
Yeah, so it's not, yeah, it's like, yeah, we localize, yeah, sorry. So yeah, like we have the yeah, like the cuspidal Hickey algebra and like this is, yeah, so something like, and also like the Hickey algebra for the all mod, and then like this particular CM family, like it corresponds to the morphism, like it's actually it's something like an anticyclotomic variable, and yeah, like we are local. Yeah, actually, like the definition of this H is just where I mean we have this H1 odd if you like on the open modular curves. So sorry, just taking like the tensor with respect to the Hickey algebra and
So Ashay, do you uh, do you prove freeness and of the representation and that it lands in the cuspidal part and so on before tensoring over to the Iwasawa algebra of K? I mean, do you get information about non-CM irreducible components as well?
yeah, actually, yeah, we don't know. Yeah, it's a quite interesting problem. Like, but maybe at least so far the method is actually quite sensitive to the CM, like
Okay, so-
for Einstein, but the CM situation.
Okay, so you only get the information on the CM.
Yeah, we actually we did not. Yes, but yeah.
Okay, then maybe since there will only be a short break for the next talk, let's say.